Hello, I'm Anil Maskey, a senior research scientist from NASA Impact Project at Marshall Space Flight Center, and also the artificial intelligence lead at the NASA Science Mission Directorate at NASA headquarters. I am a challenge co-author for GeoAI Reimagined, Transformative and Diverse Earth Science Applications using Foundation Models. This challenge features a first-of-its-kind geospatial foundation model, a result of collaboration between NASA and IBM Research. The best part, we have made this model open source through Hugging Face, making it freely available to all. I invite each one of you to join us in this challenge, where we embrace the spirit of collaboration, innovation, exploration, and inclusion, all aligned with the NASA's Year of Open Science. To guide you on this challenge, next, our colleagues at IBM Research will provide comprehensive details on Foundation Model itself and help you unlock its potential. I wish you all happy hacking and good luck.
Hi, Space Apps. My name is Lin Song, and I am a senior technical staff member at IBM Research based in Yorktown Heights, New York. So in the past few months, I'm pretty sure all of us heard a lot about generative AI and foundation models, especially in the language domain where foundation models are really changing many people's daily lives by making their daily tasks more productive. So in the past year, one question we've been asking ourselves is, what if we can apply the same idea, the same foundation model concept to geospatial science, such as Earth observation data? This is particularly important for two reasons. One, up until now, there haven't been many models out there that one could just take off the shelf and customize or fine-tune to their specific applications in Earth science. Well, there are big models available out there in related domains like computer visions, but Earth observation data like remote sensing data are more complex. Its multispectral nature makes the learning not transferred well from models trained with only RGB. And its temporal properties like seasonalities are not captured in static image modelings. Second, one of the biggest challenge about Earth science data is that the volume of data is so huge, but the amount of label data is so small, because labeling such kind of data is a very time-consuming and error-prone process. We believe foundation model is the perfect fit for this kind of data challenge, as foundation model is about training a huge self-learned model from unlabeled data, which can easily be fine-tuned to different downstream applications using very small amount of application-specific data, which massively decrease the amount of data labeling required and ultimately increasing productivity and impact. For this reason, NASA and IBM Research partnered up to create a first-of-its-kind geospatial foundation model using harmonized Landsat Sentinel data from NASA. This model, which is available now on the open-source AI platform Hugging Face, will be at the center of this Space App challenge, as we ask participants to leverage it to explore new downstream applications in areas like disaster response, environmental change monitoring, and more. Now, my colleague Daniela from our Brazil Research Lab and Paulo from our UK Research Lab will use our IBM NASA Hugging Face page to walk you through the details of the science behind the model and the tools that we provide to get started with the challenge.
Hi, my name is Daniela, and I'm a research scientist at IBM Research in Brazil. So, foundation models are large machine learning models trained with big data sets, such that with only a few adaptations, they can be applied to a wide range of downstream tasks. Let me show you how we implemented and trained our foundation models on the harmonized Landsat Sentinel data from NASA. Similar to what is done for text and natural images, we need a self-supervised approach to train the model, and data reconstruction is a straightforward task to accomplish this. It works like this. We take an input image, divide it into patches, mask some of these patches, and we train the model to reconstruct the original images. So the target is exactly the original image. The model actually has two parts, an encoder and a decoder. The encoder receives the image patches and extracts features from it. The decoder then receives those features and reconstructs the original image. If we train the model like this with a lot of data, the encoder becomes really good at extracting relevant features. And this is what we leverage when using the model for a downstream application. Once training is done, we can replace the decoder with any suitable set of layers for a specific downstream task and fine-tune the model for that task. Regarding our model architecture, it considers the multispectral and temporal aspects of remote sensing data. So our foundation model was actually trained on sequences of HLS images with RGB and infrared bands. You can access the model card on Hugging Face to see more details on our foundation model and download the model checkpoints. This can be done from the web UI or using the Hugging Face Hub library. Now, I'll pass over to Paulo so he can explain how our foundation models can be used for the challenge to target different downstream applications.
Hi, I am Paolo Fraccaro. I'm a research scientist at IBM Research UK. And as Daniela said, I'm going to give you a little bit more details on how to use the Geospatial Foundation model for the Space Apps Challenge. Let's dive in. On the IBM NASA organization card on Hugging Face, in addition to the Geospatial Foundational model that you can find here as Daniela has shown, we have a number of examples of fine-tuned models to specific downstream tasks. They include, for example, flood detection, multi-temporal crop detection, and burn scar detection. And you can really take these and the related data sets as an inspiration for the challenge. So they can be used, adapted, but they can also be an inspiration, and you can bring in your own data and applications. So to understand a little bit better what happens when the Geospatial Foundation model is used for fine-tuning and to a specific downstream task, let's dive in on one of these models. Let's take, for example, the crop classification one. All the details about the model, performance, and other details are here, but I would like for a second just to focus on this image. So to fine-tune the model, what we need is new input images. In this case is HLS data, multi-temporal HLS data, and some labels of an application of interest. In this case is a crop classification. So what happens is that we are going to reuse the encoder of the Geospatial Foundation model, combine it with a decoding head. There can be different ones. In this case is a convolutional head. And using these new labels, the CDL labels in this case, we're going to fine-tune, to train with some sort of loss to customize to our specific application. And in this case, we are providing 3 timestamps as it was originally done for the pre-trained model, for the Geospatial Foundation model, and we're using HLS. But if you go through the other models, you'll see that the model can be adapted for any other number of timestamps as both flood detection and burn scars detections. Just use one timestamp, but also different resolutions, because, for example, flood detection uses Sentinel-2 data, which has a 10 meters resolution against the 30 meters resolution of HLS. So having understood what happens, let's see in the model in action with a demo example. Each of these models have a demo page that you can use, dropping your own images, or there are also some images here for people to play. So you see now we have 3 different timestamps that are provided to the model, and in this case it's 3 different growing seasons for the crop. And this is the sort of output that you're gonna get. And you have a number of crop categories here alongside, for example, open water and others. Now, another thing that we provide that you can leverage to do the task is the code, sample code that we have used as part of the IBM NASA collaboration. This is a simplified version of what we're using, but it allows you to do everything you need for the Space App Challenge. So in this GitHub repo, you have all the details to set up your environment and to leverage the code, how to use it. And the only thing that you need to do is to get new data, new labels. You can reuse the ones that we have shown you. But in addition to that, we're leveraging segmentation as the library that we have used to fine-tune our models, and is adapting or reusing one of these config files. You have the ones that for the examples that we have shared on Hugging Face, and they contain all the information about your training, about your data, and I'm not going to go into much detail here, but you can have a look, and all the MMSEG documentation applies, so you can get more familiar with how it works through the original documentation. Once you have your config file customized for your application, then here there are simple instructions on how to leverage it to complete your task. Just train segmentation, and this is going to follow the instructions that are specified in your config file. So you have all the details about the models, you have all the details about the code, and you'll be able to deploy it on your favorite environment, IBM Cloud or others. And this is all from us. I wish you best of luck.